The mineral olivine is a magnesium iron silicate with the formula 2CO4. Thus, it is a type of nesosilicate or orthosilicate. It is a common mineral in the Earth's subsurface but weathers quickly on the surface. The ratio of magnesium and iron varies between the two end members of the solid solution series, forsterite and fayalite. Compositions of olivine are commonly expressed as molar percentages of forsterite and fayalite. Forsterite has an unusually high melting temperature at atmospheric pressure, almost 1900 degrees Celsius, but the melting temperature of fayalite is much lower. The melting temperature varies smoothly between the two end members, as do other properties. Olivine incorporates only minor amounts of elements other than oxygen, silicon, magnesium and iron. Manganese and nickel commonly are the additional elements present in highest concentrations. Olivine gives its name to the group of minerals with a related structure which includes tephrite, montichelite and kirschsteinite. Olivine's crystal structure incorporates aspects of the orthorhombic P Bravais lattice, which arise from each silica unit being joined by metal divalent cations with each oxygen in CO4 bound to 3 metal ions. It has a spinel-like structure similar to magnetite but uses 1 quadrivalent and 2 divalent cations M2 plus 2 M plus 4O4 instead of 2 trivalent and 1 divalent cations. Olivine gemstones are called peridot and chrysolite. Identification and paragenesis. Olivine is named for its typically olive-green color, though it may alter to a reddish color from the oxidation of iron. Translucent olivine is sometimes used as a gemstone called peridot. It is also called chrysolite. Some of the finest gem-quality olivine has been obtained from a body of mantle rocks on Zabagad Island in the Red Sea. Olivine occurs in both mafic and ultramafic igneous rocks and as a primary mineral in certain metamorphic rocks. Mg-rich olivine crystallizes from magma that is rich in magnesium and low in silica. That magma crystallizes to mafic rocks such as gabbro and basalt. Ultramafic rocks such as peridotite and dunite can be residues left after extraction of magmas, and typically they are more enriched in olivine after extraction of partial melts. Olivine and high-pressure structural variants constitute over 50% of the Earth's upper mantle, and olivine is one of the Earth's most common minerals by volume. The metamorphism of impure dolomite or other sedimentary rocks with high magnesium and low silica content also produces Mg-rich olivine, or forsterite. Fe-rich olivine is relatively much less common, but it occurs in igneous rocks in small amounts in rare granites and rhyolites. And extremely Fe-rich olivine can exist stably with quartz and tridymite. In contrast, Mg-rich olivine does not occur stably with silica minerals, as it would react with them to form orthopyroxene 2C2O6. Mg-rich olivine is stable to pressures equivalent to a depth of about 410 km within Earth, because it is thought to be the most abundant mineral in Earth's mantle at shallower depths. The properties of olivine have a dominant influence upon the rheology of that part of Earth and hence upon the solid flow that drives plate tectonics. Experiments have documented that olivine at high pressures can contain at least as much as about 8,900 parts per million of water, and that such water contents drastically reduce the resistance of olivine to solid flow. Moreover, because olivine is so abundant, more water may be dissolved in olivine of the mantle than contained in Earth's oceans. Extraterrestrial occurrences. Mg-rich olivine has also been discovered in meteorites, the Moon, Mars, falling into infant stars, as well as onto asteroid 25143 Itokawa. Such meteorites include chondrites, collections of debris from the early solar system, and pallasites, mixes of iron, nickel and olivine. The spectral signature of olivine has been seen in the dust disks around young stars. The tails of comets often have the spectral signature of olivine, and the presence of olivine has recently been verified in samples of a comet from the Stardust spacecraft. Comet-like olivine has also been detected in the planetesimal belt around the star Beta Pictoris. Crystal structure. Minerals in the olivine group crystallize in the orthorhombic system with isolated silicate tetrahedra, meaning that olivine is a nesosilicate. In an alternative view, the atomic structure can be described as a hexagonal, close-packed array of oxygened ions with half of the octahedral sites occupied with magnesium or ions and 1/8 of the tetrahedral sites occupied by silicon ions. There are 3 distinct oxygen sites, 2 distinct metal sites and only 1 distinct silicon site. O1, O2, M2 and C all lie on mirror planes, while M1 exists on an inversion center. O3 lies in a general position. High-pressure polymorphs. At the high temperatures and pressures found at depth within the Earth, the olivine structure is no longer stable. Below depths of about 410 km, olivine undergoes an exothermic phase transition to the sorosilicate wadsleyite at about 520 km depth. Wadsleyite transforms exothermically into ringwoodite, which has the spinel structure. At a depth of about 660 km, ringwoodite decomposes into silicate, perovskite Ca3, and ferropericlaso, in an endothermic reaction. These phase transitions lead to a discontinuous increase in the density of the Earth's mantle that can be observed by seismic methods. They are also thought to influence the dynamics of mantle convection in that the exothermic transitions reinforce flow across the phase boundary, whereas the endothermic reaction hampers it. The pressure at which these phase transitions occur depends on temperature and ion content. At 800 degrees Celsius, the pure magnesium endmember, forsterite, transforms to wadsleyite at 11.8 gigapascals and to ringwoodite at pressures above 14 gigapascals. Increasing the ion content decreases the pressure of the phase transition and narrows the wadsleyite stability field. At about 0.8 mole fraction phaolite, olivine transforms directly to ringwoodite over the pressure range 10.0 to 11.5 gigapascals. Phaolite transforms to Fe2CO4 spinel at pressures below 5 gigapascals. Increasing the temperature increases the pressure of these phase transitions. Weathering. Olivine is one of the weaker common minerals on the surface according to the Goldnich dissolution series. It weathers to idingite readily in the presence of water. The presence of idingite on Mars would suggest that liquid water once existed there, and might enable scientists to determine when there was last liquid water on the planet. Uses. A worldwide search is on for cheap processes to sequester CO2 by mineral reactions, called enhanced weathering. Removal by reactions with olivine is an attractive option, because it is widely available and reacts easily with the CO2 from the atmosphere. When olivine is crushed, it weathers completely within a few years, depending on the grain size. All the CO2 that is produced by burning 1 liter of oil can be sequestered by less than 1 liter of olivine. The reaction is exothermic but slow. To recover the heat produced by the reaction to produce electricity, a large volume of olivine must be thermally well isolated. The end products of the reaction are silicon dioxide, magnesium carbonate, and small amounts of iron oxide. The aluminium foundry industry uses olivine sand to cast objects in aluminium. Olivine sand requires less water than silica sands while still holding the mold together during handling and pouring of the metal. Less water means less gas to vent from the mold as metal is poured into the mold. In Finland, olivine is marketed as an ideal rock for sauna stoves because of its comparatively high density and resistance to weathering under repeated heating. In cooling, olivine is also used to tap blast furnaces in the steel industry, acting as a plug removed in each steel run.